Let's get going. Good afternoon, everybody. Welcome to another sunny afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Some important announcements. First of all, a week from this Wednesday will be test four. Test four. And I'll talk more about it on Wednesday. By Wednesday, I'll put out an email, an announcement with the point breakdown and everything. But test four will cover uh, fats and oils, the lipid chapter, and carbohydrates. And that will be that. Also, if you looked at it, next Wednesday, a week from this Wednesday, the 5th, is the deadline for the extra credit project. Remember, the extra credit project is optional, but if you do it, it's 10. Yes, 10. 10 points. Now, as I mentioned when I talked about it, and you can find it on D2L, uh, if you email me or if you stop by my office hours, which I'll have it tonight and Wednesday night, starting at 6, I will check it over. And if anything's wrong, I'll help you correct it, which means if you take the time to do it, you can get, yes, 10. 10. Yes, I still have 5 fingers on each hand, 10 points. Uh-oh, it's starting to be a pretty awful humor Monday. But anyways, don't forget that. Also, if you haven't, I think most of you have, but a couple haven't, make sure you turn in your labs on time. As of yesterday, I'm pretty much caught up with everybody's labs that you've turned in, checking D2L to make sure if you handed in a lab, I have graded it. Well, in that case, let's get going. Did anybody happen to look around your house or different things and think, is it chiral or achiral object? Like your hands are chiral. Anything that has left and right in this thing is probably chiral. Remember, chiral, non-superimposable mirror image. Achiral, superimposable mirror image. Your hands are mirror images, they're not superimposable, and therefore they are chiral. Let's see, what do I have around here real quick? I don't have anything real quick. Trying to find some, this would be superimposable with its mirror image. And it's superimposable. So Post-its with nothing written on them are superimposable. Therefore, they're achiral. Oh, I could put that on a test. I gave it away already. All right, let's get back to work or fun. Now, if you remember, I was talking about enantiomers. Enantiomers are non-superimposable mirror images of molecules. And if a molecule has a non-superimposable image, it has an enantiomer. As we did last time, draw the enantiomers of a couple of sugars I had. And here's glucose. And let's start out with a little fun. Oh, I haven't done it, and I figure Wednesday would be a good day. I think it's better Wednesday. Wednesday, I'll go through the lipids problem set, fats and oils. Thumbs up, people. You see my whiteboard? Thank you. here's one for you to start out this nice, beautiful day. Tomorrow is supposed to be nice and warm. I wonder if I'll have to turn on my air conditioner or not. I've got it uncovered. But anyways, draw the enantiomer of that compound. 3 points each. And for those of you who came in late, don't forget, it's still, I've expanded it to a month, not a day. It's National Turn on Your Webcam Month for Dr. White. Please. That way I can see your real pictures. People, I can see your pictures on my screen, so you're alive. They're alive. Yay. Good news, I don't think I killed anybody this semester or last or the others by talking about organic chemistry or any other way either. I hope you all had a nice time since we last met. All right, thumbs up, people. Everybody done? I think everybody's done, so I better get to work. Now, what is the enantiomer of a compound? It's its mirror image. Now, I like to draw in the mirror because it's a mnemonic device, memory, or it helps me. You don't have to, but achiral carbons, you don't have to draw the mirror image. But if you wanted to draw this one here, like this, that's fine. Same thing down here. If you wanted to draw this, that's fine, but you don't have to. But these are chiral carbons. Remember, chiral carbon, four different groups, 4 different atoms, or a combination of 4 different groups and atoms. Same thing here. So if we look at this hydrogen, it's closest to the mirror. It's what we'll see first. The hydroxyl group is farthest away. This hydroxyl group is close to the mirror. I'm a little off base here, and I think I drew it wrong. Hold on. So used to doing glucose. Oh, Dr. White messed up. All right, hydrogen closest, hydroxyl group farthest away. Next carbon, hydroxyl group closest to the mirror, what's farthest away, hydrogen, that's what you'll see. And finally, bromine, closest, farthest away, hydrogen, and that's how you do an enantiomer. And I mentioned diastereomers, which I'll never ask on a test, are stereoisomers whose molecules are not mirror images of each other. Cis and trans are an example of that. Now, I talked about Fisher projections, which I will not put on a test. Here's 3-dimension, draw Fisher. I should ask my thumbs up, people. Can you see that on the screen? Thank you. Now, one thing I should ask, which I think we might have done, you don't have to learn the structure, but this is glucose, and we'll talk more about it today. And I would ask you, circle the chiral carbons. Remember, each intersection of a line is a carbon here, here, and here. So why don't you circle the chiral carbons? And all of you have your camera on. Thank you. Oh, it warms my heart. Things that warm my heart are good things. Remember, chiral carbon has 4 different groups, 4 different atoms, or a combination of each. If you're done, give me a thumbs up. I think everybody just gave me the thumbs up, so I better get to work. All right, if we look at this carbon, it has hydroxyl, hydrogen, this aldehyde, and the rest of the chain. That's 4 different groups. Same thing with this carbon, hydroxyl, hydrogen, these 2 carbons, and these 3. That'd be 4. And if we look at this one, same thing, 4 different groups, and this one, 4 different groups. So in glucose, there are 4 chiral carbons. Now, one of the things I won't put on a test, but I think it's interesting to know about is stereoisomers, both enantiomers and other things, diastereomers. Let me go to the whiteboard, I got more room. And hopefully everybody, did you see my whiteboard? This won't be on the test, but I thought it'd be interesting. If N equals the number of chiral carbons in a molecule, then the number of stereoisomers is 2 to the N. Now, glucose has 4 chiral carbons, 2 to the 4th power is 16. That means glucose type molecules, there's a possible total of 16 stereoisomers. One of them is its enantiomer, and then the other 14, the original enantiomer, other 14. Mother Nature only picked glucose as what she uses, where she had 16 possible isomers, she only picked 1. And that's how good of an organic chemist Mother Nature is. I mean that sincerely. Now, because when you have a chiral carbon or more, the molecule is chiral, meaning it can exist in right or left form. And in order to detect that or talk about certain monosaccharides, mono 1 saccharide, carbon, sugar with either aldehyde or ketone, and the switch is off for here, but you may need this for other classes. There's the DL designation. And this works based on the left or right of the highest numbered chiral carbon with the hydroxyl group. In an aldehyde, which really this is 1, 2, 3, 4, 5, 6. This is not chiral. So this is the highest number. If the hydroxyl group is on the right, we put a D in front of the name, D-glucose. If we're on the left, it would be L-glucose. And let me do one more thing, and then I'll come back to this. And again, switch is totally off. This will not be on test. Now, when we talk about enantiomers, they're non-superimposable mirror images. And turns out they have all the same physical properties except two things. And one of them is how it's called optical activity. And the other one, again, switches off now, the reactivity, how it reacts with other chiral compounds, which turns out to be very important. Now, what is optical activity? And how many of you are familiar with plain polarized light? Light, like hitting me right now, ouch, that was an awful joke. I'll never use that again. But anyways, light that's hitting you comes in as waves. Light can be a particle and a wave. It can be both at the same time. I'm not a physicist, so I'm not going to explain why. But think of it as waves. And the light, white light, coming in at this way, it can come in at this way, actually comes at you, the waves 360 degrees. Well, it turns out scientists, chemists, have found that if you use a filter, you can just have one wave come. Does that look like it's coming right at you? One wave, not all 360 degrees. How many of you have ever seen or heard about plain polarized sunglasses or polarizing sunglasses? And they're pretty strong, work quite well. How? Because they're essentially, they filter out all the polarized, all the light except one wave, one degree. And that means most of the light is filtered out. And that one wave we call plain polarized light, you're putting it through a filter because it polarizes it. Now, when we talk about optical activity, a chiral molecule is an optically active compound. And what does that mean? It rotates plain polarized light to either the right or left so many degrees if you have one wave. So if you have a sample of stuff here and you put in plain polarized light, it will rotate it if you had a detector where it was coming in on the detector at 0 degrees, it might rotate that light to the right or left, say 10, 15 degrees or more. And this is an important way of telling, do you have an optically active compound or is it impure? If you know it's pure, it should go so many degrees right or left, and it doesn't at a certain temperature, guess what? You don't have a pure substance. Now, when we talk about optically active compounds, again, switches off, but this might be useful for your other classes. You can rotate, if it's coming in at 0 degrees like this, you can rotate it to my right or my left. And there's no way of knowing what it will do until you go into the lab and measure it. You just can't say, look at a molecule and say, which way will it rotate plain polarized light? And when it rotates to the right, it's called dextrorotary compound. And dextro, I believe, comes from Latin for right. And you use a plus sign to designate that. When it rotates it to the left, it's levo or levorotary. I don't know, I'm not a sure chemist. And you use a minus sign to show that. Now, quick Dr. White story. A couple of years ago, I had this one woman who was coming back to get her master's degree in nursing and needed to take organic again because it had been so many years since she took it. At this point, she said, "Oh, that explains the letters and symbols on the feeding bottles for intravenous feeding." And if you've ever been in a hospital where they feed you intravenously, I did when I had a major operation. I think I told you about my double hernia. Yeah, I did. We talked about inhalation anesthetics, ethers. But anyways, on the bottle, it has glucose because that's usually what they inject intravenously or feed people with. And on the label, it has something. Let's go out into the real world. I was just getting something. All right, I think I might have mentioned it before. Does everybody see the right here, the plus D glucose on your screen? And this is from Sigma Aldrich, which is not for medical use, but Sigma Aldrich is finally probably the finest company in the world for getting smaller samples of most organic chemicals, and others too, but mainly organic. They're located in Milwaukee. I think I first started ordering from them in the mid 1970s. Oh, I shouldn't have said that. But anyways, they are great. And notice you see D plus glucose. D tells you the hydroxyl group on carbon 5 is on the right. The plus sign tells you it rotates plain polarized light to the right. Let's see something. They give you information and more things you can learn about it. Oh, that one was discontinued. But anyways, I just wanted to show you that that's an important thing. All right, let's go back and talk about chapter 16 again. And here, I'm going to turn the switch off briefly, but these are things you may need in your other classes, so that's why I'm covering it. Notice we have an aldehyde here. As I mentioned beginning of this chapter, that you can write an aldehyde like this, or which my software does for sugars, like that, same thing. And here we have an aldehyde. Now, when you have a monosaccharide that's an aldehyde, they call it an aldose. Again, switches off, and this is called a hexoaldose because there's 6 carbons, hexane, like hex. And this is glucose, by the way. Again, I'll never ask you on a test what's the structure of glucose. Next, if you have a ketone in a monosaccharide, it's called a ketose. Why they need that, I don't know. And here's my ketone, here's R prime, and we could say this whole thing is R, or the other way around. So this is a ketone, and we call it ketose. How many of you ever heard of ketosis? And that's the problem with diabetics, where they have too much sugar, I believe, don't quote me on this, or it turns into ketones, and don't really quote me on this, but this is how it got its name from ketosis. Ketosis. Interesting story about, I think it was 3 summers ago. I had 2 students, and first day in lab, where I'm walking around talking to them everything, I see each one has this big thing on their arm right around here. And being the nosy person I am, and Dr. White can be very nosy, I walked up to one of them and asked, do you mind asking you what's that? And he says, no, that's my glucose monitor that feeds to my cell phone by Bluetooth. And therefore, I don't have to take a blood sample to measure my sugar level. I said, oh, that's neat. Be careful when you're in the lab. Try not to get any chemicals on there or any time on you, period. And I had 2 students, and they both had were diabetics. One of the things I did, I asked them in private, and I've been doing this for many years, when I find out a student has a certain medical problem, or I don't know, problem situation, I ask them if there's an emergency, first of all, how do you want me to handle it? And second of all, do you have in your purse, backpack, or something, a phone number for emergency? And I've had people who are epileptic, and they told me if I go into a seizure, they explained what they want me to do. And one of them, because they didn't have insurance, unfortunately, she didn't want the paramedics called because she couldn't afford to go to a hospital. Well, luckily, none of them ever had a seizure, but I think that was my responsibility to be someone who could help them in an emergency, which I was prepared to do. And by the way, I've talked about this as sugar, and this is something you should know. A sugar is a general designation for a mono and disaccharide. So if you're at a dinner with someone, they say, please pass the sugar, guess what? They're talking about either a mono and disaccharide. Now, there's a special sugar you should know. First of all, I'll wait until you copy that down. Everybody got it? Okay. I don't have it on here, but you should know that table, I think I mentioned this earlier. This is not an IUPAC name, it's a common name that everybody uses. Table sugar is called sucrose, and I'll talk more about today what's the structure of sucrose. And so table sugar is a sugar because it's a disaccharide, which I mentioned earlier. I'll never ask you is sugar a disaccharide, but you should know that. And it's called sucrose. Now, forget about this right now. I'm going to come back to this in a little while. Switch is sort of semi-off here, but I thought I'd just fill you in a little background. This is D-glucose. D because the hydroxyl group right here on this highest number, chiral carbon, is on the right. I'll never ask that on a test. Turns out D-glucose is the most abundant sugar in nature. It's the sugar in your blood. And this molecule helps bring, I guess, nourishment. Now, Dr. White's well beyond his knowledge of the human body, because last time I took biology was freshman year high school. But anyways, this is the sugar in your blood. It's an allohexose aldehyde with 6 carbons, and it rotates plain polarized light to the right. This I will never ask on a test, but I thought you'd like to know that. Now, another sugar I just like to talk about, I won't have this on the test, is D-fructose. How many of you have heard of high fructose corn syrup? All you gotta do is look at a bottle of ketchup or a lot of other things. And this is a ketohexose, ketone, 6 carbons. This turns out to be the sweetest sugar in nature. It's much sweeter than sucrose. Now, it turns out, and I'm not going to ever ask this, it rotates plain polarized light to the left. It's D-sucrose, because this hydrox group is on the right, the highest, and I won't ask that. But it's found in corn syrup, or you can modify corn syrup so it has a high level of D-fructose. And for those who are not familiar with the food industry, I don't know how many years ago, 10, 15 years ago, I might be off by a couple of years, uh, organic chemists, not me, but found a way to modify corn syrup so it was extremely high percentage of D-fructose. That meant it was super sweet, and corn syrup is super cheap, a lot cheaper than table sugar sucrose. And most of the food industry, where they would use sucrose right here, switch to cheaper D-fructose. Now, I won't talk about it now, but maybe later today I will, or next Wednesday, this Wednesday. A lot of the mothers groups and other concerned citizens have come out and said, oh, D-fructose is causing a lot of the problems in our children, and it's dangerous. And they had a whole list of diseases and Dr. White doesn't believe that. I'll explain why, yes, having this high is not a good thing, but it's not just the D-fructose. Now, just like here, D-glucose can form a cyclic form, and I'll get to that. D-fructose can form a cyclic form here. Now, these cyclic forms that I'm showing you are called Hawthorne projections. And the first time I tried teaching organic at ECC, I tried teaching students what this means. This is a three-dimensional molecule where you show two dimensions, show it on paper this way. And students had the worst problems. I realized it wasn't worth the effort to spend time on something nobody could master. I even have a little difficulty. So I just wanted to mention it's called Hawthorne projection. It's a two-dimensional structure notation that specifies three-dimensional structures of a cyclic form of a monosaccharide. Good news, it won't be on the test and won't ever be on a final. All right, now let's talk about the cyclic form, because this is very important. But it's time to show how Dr. White came up with a better way of teaching you, the students, that. And first, remember I promised a long time ago, no new reactions? Wasn't that long ago, at the end of test number 3 material. So let's look at something from test number 2. And test number 2, you take an aldehyde or ketone when R prime is H, it's an aldehyde when its carbon's a ketone, react it with an alcohol and acid. What happens? Keep your eye on the carbonyl carbon, that attacks that. And what you get, what's attached to that carbonyl carbon, R prime or H and R double prime, this becomes an alcohol and oxygen. And this is from test number 2. No new stuff. I'm going to draw the aldehyde here like an aldehyde that an organic chemist, not a sugar chemist, now it turns out one thing I haven't talked about is reaction rates. We talked about adding catalysts to make it go quicker. If you notice up here, I'm adding an acid catalyst. But it turns out, let me finish writing this molecule because it's half done. That's not polite. Now it's done. That when you have a reaction involving starting materials that are in the same molecule, called intramolecular reaction. It goes a lot quicker, and usually you don't need always a catalyst. When you have separate molecules intermolecular, then a lot of times you will need a catalyst to make it go quicker. How many of you have ever taken an international flight? Dr. White has gone to Europe a lot on business, and that's when you go between two countries. And intra would be if I took a flight inside the United States, even though they don't call it. Now, let's look at something specific. This carbon right here, it has a hydrox group on a carbon. It's an alcohol. Here's my carbonyl carbon. And this will come on and attack that just like up here. Now, instead of having students draw the Hawthorne structure for the reaction product like I had in the slide, I came up with a better idea. All right, first of all, what's not involved in the reaction will not change. You've learned that. So I'm just going to redraw it. Now, the carbonyl still has the hydrogen, just like here. It's still bonded to this part, which would be here. But now this oxygen, which is this oxygen right here, will bond all the way to here. This is an actual bond. Here, this is an arrow showing where the electrons, and this will open it up to this hemiacetal. And this carbon here is this carbon here. So this reacts to form the cyclic form of glucose. Now, couple things. First of all, if I put on a test this, you should know how to get to this product. If I put the product on the test, you should know how to get to the starting material. Why is this important? Because if this didn't happen, we wouldn't have any carbohydrates, which you know as starches, on our planet. We wouldn't have also any trees or grass or anything growing. Is that important? You better believe it. Oh, I was just going to do a generation gap thing. I will. You bet your sweet Bippy. Nobody knows what TV show that came from. It's called Laughing. Go to YouTube someday. Anyways, you should know. Let's go through this. Aldehyde or ketone, alcohol, acid catalyst. And by the way, that's bonded to there. Hemiacetal or ketal. Now, when it's intramolecular, we do not need the acid catalyst, and it's in equilibrium. Here's the hydroxyl group right here. And this attacks that carbonyl carbon, which I show you right here. And it opens it up to what you see right there. And you should know how to do this. And by not having you learn the, by the way, this longest world's ugliest carbon oxygen single bond is this one right here. And this goes from this atom bonded to this atom. Here I'm just showing electrons, so you don't put an arrow on this side. You're actually showing a bond. Is everybody clear on that? And why don't you try it? What would be the product of that reaction? And I'll help you out today. All right, if you're done, give me a thumbs up. All right, looks like I saw a lot of thumbs, so I better get to work. Now, here's my carbonyl right here, and it's always the hydroxyl group on C5. 1, 2, 3, 4, C5. And that hydroxyl group, alcohol really, will attack here to form this bond and open up the carbonyl carbon to a hemiacetal. Whatever is not involved in the reaction, I'm just going to rewrite because it's not going to change. However, this oxygen right here will react to the carbonyl carbon to form a carbon-oxygen bond, this one right here. So instead of asking you to learn Hawthorne projections, here's the world's ugliest, longest carbon-oxygen bond. That's this right here. Here's my carbonyl, which becomes this carbon, and will also have an alcohol on it. And that's how you make the cyclic form of glucose, because this molecule here, which I'll never ask you on a test to draw glucose, but this is glucose. Now, instead of rushing, I'm going to do something a little different. Let's take our 5-minute break now, come back at 1:50, and we'll continue. Dr. Wood's going to get up and stretch. I'll see you in 5. Oh no, I'm late. Time to start again. All right, everybody back. Apologizing for being a minute late. Mail came and so did something from Amazon. Sort of like getting a gift. Not really, I bought it myself, but it's always nice to get stuff you buy for yourself. But anyways, which is easier? To see this and have to write this, or do it this way? I hope you all agree, at least I've found from experience for students, this is the easier way. And don't tell anybody I'm being nice. Shh. But anyways, that's for glucose. Now, if we go back and we look at fructose, now fructose is a ketose, but it's a ketone. And hold on a second while I write this down, because I always remember glucose. I get one of the hydroxyl groups on fructose wrong. So I'm cheating now, not really. All right, let's get to work. Now this can form a cyclic form also, which looks like this, which is also a Hawthorne structure, which students get confused by. So once again, Dr. White to the rescue. Let's take a look at this one. Now remember, there's a carbon there. And this is fructose. And it's in equilibrium with its cyclic form. And again, let me remind you, you have a ketone or aldehyde plus an alcohol. If you have separate molecules, you need an acid catalyst, and this attacks my carbonyl. What's attached to my carbonyl? Our prime can be hydrogen or carbons, and it's either a ketone or aldehyde, and this opens up to this, just like we saw before. However, now, where's our alcohol? Turns out in fructose, it's the same alcohol, the hydroxyl group on carbon 5. And here's my carbonyl, this right here. And now this attacks that carbon, just like this attacks the carbonyl carbon. And what's unaffected, not involved in the reaction, I'll rewrite. Okay, and this oxygen right here will be bonded to the carbon. This one right here, that's this one right here, and this long bond here is this bond right here. And what else will you have on that carbon? A hydroxyl group. kind of test. If I were to give you this, you should be able to write the structure for the product. If I give you the product, you should be able to write the starting material. And if this didn't happen, we wouldn't have any table sugar. Oh no, that wouldn't be good. So is this important? Well, in my book, having both high starches and table sugar, disaccharide, is pretty important. And you should know how to do this. So I'm going to let you try it on your own. And let me write down here in case you forgot. If it was intermolecular, you need an acid catalyst. And there you go. Oh, did I tell you the closer it gets to June, the uglier my hydrogens get? That's better. And when you're done, give me a thumbs up. I think everybody's done because I saw a lot of thumbs. So I better get to work. Now, in either glucose or fructose, it's always C5. This would be 1, 2, 3, 4, 5. Carbon number 5, organic chemist shorthand is C5 carbon 5. And this is this alcohol, which attacks the carbonyl carbon to open it up and form this bond. So this will attack my carbonyl carbon right here. And that's the only thing involved in the reaction. And it'll open up to this carbon. So what's not involved in the reaction, I'll rewrite. That's not hard. This carbon is this carbon right here, which is this carbon. And Dr. White made a mistake, which I can erase immediately and fix. And this oxygen here is this oxygen, which is bonded to my was the carbonyl carbon. And notice it has a hydroxyl group on there. And this is a cyclic form of fructose. And you should know how to do that. Now, next, let's talk about reductions. I haven't used terminology of reactions. Reductions is also one type of reduction, is hydrogenation. And says, see board, well, I better get to work. I'm not the board, so let's get the board on there. Long ago, test number 2 material. If you take an aldehyde or ketone, and I better ask, everybody see my whiteboard now? Thank you. And you have a pi bond, which you break. What's attached to carbons? You don't break carbon single bonds, but you break the pi bond, and each atom of the double bond gets a hydrogen. This is called hydrogenation. It's also called the reduction, or you reduce the aldehyde or ketone. It's interesting. I always remember glucose, but fructose. Now, this will not react with an alcohol. And I'm going to let you have some fun right off the start. What would be the product or products of the following reaction? Ooh, I just learned how to make your pictures bigger on the screen, which I'll undo now. Somebody give me a yes or no with your head. Have I talked about Barkeeper's Friend in this class yet? Did I talk about hair and grease removal product in this class yet? All right, we got time today. Bad, Dr. White. All right, let's do this. I think everybody's done. What do we have here? Well, we have an aldehyde, hydrogen, and a catalyst. Here's the general reaction. You're not going to break carbon-carbon single bonds. And what's not involved in the reaction, I can just rewrite. Now the carbonyl carbon, which is this carbon, you break the pi bond, and each atom gets a hydrogen. And I can rewrite this if I wanted to. You don't have to, but there's a reason why I'm doing it. And this is another way of writing it. Now, this molecule has a common name, sorbitol, OL. It's all alcohols. There are actually 6 of them. And let's go out to the real world right now. Everybody see sorbitol on your screen? All right, I'll mention it again that Wikipedia is so heavily policed in chemistry, especially organic chemistry, that whatever you find is generally correct. Now, sorbitol has this structure they show right here. Every bend in a line is a carbon. 1, 2, 3, 4, 5, 6. This shows stereochemistry like the Fischer. And this is what you just made. Now, what is it used for? Good question. And sorbitol is a sweetener, and it's made by the reduction of glucose, taking glucose and reacting with hydrogen in a catalyst, and it's a sweetener. And one of the places you find it in is diet foods, because it's hard for your body to break this down. Therefore, it's low calorie. And the other place you'll probably find it, let me do this. If you go to your local big box store or drugstore, and you know how most of them, like all of them, sell over-the-counter stuff, medicine, like cough syrup and other things. If you look at the cough syrup, if you look on the label halfway or near the end, you'll see sorbitol. Now, there are 2 reasons they put that in there. One, it adds some sweetness without adding calories, which, oh, I'll take that stuff, it's sweet. And they do that in a lot of medicines over the counter. The other thing is it's very thick or viscous, like honey. Therefore, when they put it in with other liquids, what you're buying is thicker. And you've been conditioned, ooh, it's thicker, that must make it better. No, but you've been conditioned that. And they do things like that. That's a secret, don't tell anybody. All right, now the words on this slide, glucoside formation from monosaccharides, will never ask on a test. Now, a glycoside is the acetal ketal form from a monosaccharide. That's what we just made. And for glucose, and don't ask me why they have all these interesting names in sugar chemistry, because I'm not a sugar chemist, a glucoside is the glycoside formed from glucose. If you're confused, hang in there. This won't be on a test. And oh, look, Dr. White wrote himself a message. Remember the reaction with methanol. Thank you, Dr. White. I'll remember it now. So what does this all mean? Remember I promised no new reactions? Well, I sort of semi-lied to you. Back in, everybody see my whiteboard now? Thank you. Back for test number 1. Test number one, test number two, I mean. I showed you this reaction and you learned it, and you did quite well in test number two. Thank you. Now, what I didn't show you was the mechanism. Now, what I'm going to show you, I'm never going to ask on a test, but I want to use it to explain the new reaction, which is just really a slight wrinkle. I like that slight wrinkle on the old reaction. This one right here, which is not old, but something you learned in the past. Well, what happens? The first alcohol and acid react with the carbonyl carbon. You learned this reaction, we just talked about it, to form a hemiacetal or hemiketal. Then the second alcohol reacts with the acetal or ketal, and guess what? It replaces this hydroxyl group with this one. So you go from the hemiacetal or ketal to the acetal or ketal. And that's what I taught you. I didn't show you this. Now, as you learned from test number two, and just now with the sugar, this hemiacetal or hemiketal, you can isolate alone. So what does that mean? And here's the new reaction. Remember the one with methanol, that was my note to me. And this, the switch is on full. Here we have a hemiacetal or hemiketal, and now instead of the same alcohol up here, this gives you a symmetrical acetal or ketal, where the alkyl groups on the oxygen are the same. You can also start with the hemiacetal and react it with a different alcohol. That's why it's triple prime acid catalyst, and we get an unsymmetrical. And this is an unsymmetrical acetal or ketal, where the alkyl groups on the oxygens to what was the carbonyl carbon are different. So now let's take a look at one real quick. And the question would be, give the organic product or products for the following reaction. Notice this is this. We have my alcohol and acid. So here, this is my R triple prime. If we look here, what's attached to that carbonyl, except for the hydroxyl group, is still attached. So I can look at this and say, R prime is hydrogen. This is our double prime, and this is R. And my reaction general tells me this alcohol will be bonded like that. Oops. And what is our triple prime? And you get that. And that's how you do it. Now, why am I talking about this in carbohydrates? Well, first of all, is everybody clear what's going on? Anybody have any questions? I'll look down at the chat. Nope. All right. Now let's look at how this applies to carbohydrates. And here we have the cyclic form of glucose. What do they call it? The glucoside, which I'll never ask on a test. And if I were to react this with methanol, the reaction we're really doing is this. What's attached to that carbon in the hemiacetal, hemiketal is still there. You replace the hydroxyl group with OR triple prime. Well, in this case, here's my R triple prime methyl, and the only thing you'll change is this hydroxyl group, which is this hydroxyl group. What's ever not involved in the reaction stays the same. 2 days later, but there are a lot to write on these molecules. This all stays the same. The only thing that changes is this to this. So O, and what's R triple prime? Methyl. And that's how you do it. Again, this right here is this right here, and this is making an unsymmetrical acetal or ketal, and this is what you get. And this carbon right here is this carbon right here, which is this carbon right here, which is this carbon right here. The original oxygen carbon, this bond right here, was this, which is this, which was that. Now, which is easier, drawing this or the Hawthorne? This one. And let me give you one to try. Oops. Oops. Aren't you glad I'm not having you draw Hawthorne rings now? I am. Let me draw a longer arrow here. And your turn. What would be the product or products of the following reaction? right. If you're done, you know what you do, don't you? I think, oh, not everybody's done yet. Everybody done? Yep. All right, let's take a look at this. What do we have here? Oh, hey, with this right here, the cyclic form of glucose is a hemiacetal, where R prime is hydrogen. This one right there. This carbon has a hydroxyl group. This carbon, oxygen, right here, and R. Then we're reacting, what's this carbon-carbon alcohol, R triple prime. What's attached to that carbon is still attached. The only thing that changes is this becomes this. Therefore, the only thing that's going to change is this. Therefore, everything else I can rewrite, and I will. Don't break this bond. It's not broken. It's this one right here. And the only change is OH becomes O. And what's my R triple prime? And N-propyl. One thing, the carbon with the hydroxyl group will be the carbon attached to the oxygen. And that's how you do it. Now, I'm going to be writing something on my whiteboard. You do not have to write it down. And if we were in a face-to-face lecture in a classroom at ECC, I'd be telling you the same thing. But this is something important I would like you to watch. And I'll never ask you to do this on a test. Now, I would be saying right now in the classroom, bear with me, it will take a little while. And I can say that now too. And no, you're not seeing double, thinking. And you're not seeing things in triplicate. Well, you are actually. All right. Now, if you look at right here, you have glucose in its cyclic form. And same thing here and here. Now, over here, we have the Hemi Acetal. Everybody see that at the bottom of the screen I'm writing? What you just learned. Haste makes waste. Slow down, Dr. White. Okay. And this is what you just learned. Now, if we come over here, here is this carbon. And over here is this alcohol. And this reacts to there and forms a bond between the oxygen on the alcohol and what was the hemiacetal. Well, in real life, what happens is this forms a bond there. And this R triple prime is the rest of this molecule. Now, if we look at glucose number 2, again, we have my hemiacetal, and we also have this alcohol. And guess what? They can do the same reaction. And this forms here. And if I had another glucose, I could do the same thing, and I could keep on doing that. And I can put a lot of glucose molecules together to form what? A polymer. And what is that polymer? And as you learned in earlier this semester, polymers are like boxcars hooked together in a train. And here you can have a lot of glucose molecules, and N can be big, 50 or more. And we have a name for this when you hook a lot of glucose molecules together. And what do we call that? Starch. And this is something you should know. Starch is many glucose molecules linked together. So if I were to take glucose and react it with an acid catalyst, otherwise known as an enzyme, what I'll get is starch. And you should know this. And I can put like 50. Oh, hold on. Dr. White just did an organic chemistry chemist thing. You don't balance equations, but another way of thinking of it is lots of glucose react together to make starch. And the next time you have a potato chip or potato, rice, or any other thing, piece of bread, the glucose Mother Nature makes, let me spell it right, glucose, is react together to make starch, which is how plants make that. And that's amazing. I bet you didn't think of starches are really a polymer of glucose. So next time you're at a Zoom party and people are eating potato chips, or you go to your favorite hot dog or hamburger place and get some French fries, think about that. Those are polymers of glucose, Mother Nature's polymers. And that's all because this happens to make the cyclic form right here. And no, we don't use regular alcohols. The other alcohol is another glucose molecule. So that's where it all comes together. And don't you have to take your hat off to Mother Nature for being one heck of an organic chemist to come up with all this? hang in there. I don't know why it does in the afternoon, not in my morning class. Probably. Yep. Luckily, I can get it back. All right, so we were right here. Now, I won't ask you to hold on. Everybody see sucrose on the screen? All right, this is a structure of sucrose. Now, this is to Hawthorne, and what it really is, and this you should know, is glucose bonded with fructose. And the hydroxyl group from the cyclic form of fructose bonds with, as an alcohol, with the cyclic form of glucose. Now, this part you don't have to write down. This you should know. What is sucrose? It's a glucose and fructose molecule bonded together. And it's the same chemistry I just showed you, the same type of linkage to form an acetal linkage. Let's go back to everybody see my whiteboard with the blue and red and everything else? This right here is an acetal linkage. In other words, part of an acetal molecule. Same thing here. And between each of the glucose molecules, we have an acetal linkage. And similar in sucrose, which is a disaccharide, you have a glucose and fructose. Now, you can say, thank you, Dr. White, for not making me memorize this, but this you should know, that sucrose is really a glucose and fructose molecule bonded together. And the next time you look at that little white stuff, the white powder, crystalline material, you put in your coffee, tea, or whatever. I like it in my tea in the morning. And I guess you could put it on your oatmeal. Captain Crunch has got a lot in there. But anyways, it's two molecules bond together like this, and they're acetal, and the linkage between them is acetal and ketal. Now, polysaccharides contain many monosaccharides linked together in glucosidic, in other words, acetal or ketal. Mostly our starches are acetal. So next time you pick up a piece of bread, you're looking at a polymer of glucose, otherwise known as a polysaccharide. And I hope I didn't ruin it for you. The next time you pick up a French fry or have a baked potato, you're eating a polymer. I bet you never thought of that. And if you're with some people, you're having dinner, and they're eating that, don't mention that to them. You don't want to ruin their dinner, unless you want to. And starch, like I said, is a polysaccharide. Now, there's another type of starch, which I won't ask this on a test, but it's called amylose. And amylose is, well, actually the main starch is amylose, where you have the 1,4 linkage. And what do we mean by 1,4? This won't be on a test, but for those of you who are planning on a career in nutrition or whatever health major, it's similar, 1,4 amylose. And if we go back to my whiteboard, notice this is carbon 1, this is 1, 2, 3, 4. So this is called the 1,4 linkage. Now it turns out some starches have part of it 1/6, where this is more linear, 1,4, 1/6 can be more branched. And we have a name for that, which I'll never ask you on a test, but I thought it'd be cool to tell you about it. And that's called amylopectin. Anybody hear about amylopectin ever, these names? And that's a both 1,4 and 1/6. So there's some branching. And branching affects the nature of that starch when you cook with it, which is important to know what's going to happen with the starch. In other words, flour or other things you cook with. Now, if I look at the clock, we got about 5 more minutes. And before I go on to the next section, I figure let's take a break now, come back in 5 minutes at 2:45, and we'll continue on. I'll be back. Ouch. Uh-oh, was running late again today. I gotta fix my watch. Oh, I don't have a watch. No wonder. Time to start. All right. Now, we're getting into the exciting part of the semester, and we've already done some of it, because we're talking about things you've learned and how they happen or occur. The general chemical reactions are occurring all around you in nature and inside of you too. Now, I talked about how starch is just a polymer of glucose. And notice the linkage between the different glucose molecules in starch is an acetal linkage. So what does that mean? Oop, wrong. And I'll come back to this. What happens when you chew and swallow something with starch in it? Did I tell you when I was about 2 years old, my mother said, chew your food before you swallow it or you'll choke? And guess what? I found out she was right. In case you were wondering, I survived. But anyways, after you chew something with starch, where does it go? Down your throat, into your stomach. What's in your stomach? Acid and water. And let's look at a reaction you learned a long time ago. And for test number 2, he took an acetal or ketal, reacted it with acid and water, hydrolysis of an acetal or ketal, acid hydrolysis. You get back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol. And if you remember, I put 2 there, you don't have to balance it, and that's what you get. Now, let's look at, first of all, let everybody copy this down again. And remember, if I ever write something too fast to move on, a good question is, hey, could you please go back to that? I haven't finished. And I always say yes. Everybody got this? All right, now, if we look here, each one of these, this oxygen, this is the alcohol, this is the other alcohol, and this is my acetal. And you break that. Now, what I'm not going to ask you to do is write that, but you should know. Switch is on. Write the name of the product you get when you treat starch with acid and water. I'll give you 8.2 seconds to think about it. That's my turn. I see everybody's enjoying their lunch or snack out there. I once, oh no, I forgot. Something I wanted to forget, I just remembered. I was walking down the hallway years ago at ECC, and there was an instructor lecturing while eating a banana. Come on, give me a break. How can you eat anything in the lecture? That's not polite. But anyways, back to this. What's starch? It's glucose linked together. And when you break it apart, think of the alcohol and the aldehyde linked together, and we get glucose. So when you eat any starch, your body, your stomach, and I think it's your large or small intestine, don't quote me on that, makes glucose. And remember, glucose is the most abundant sugar around. Why? Because our body makes it. in your blood. It's the sugar that's transporting to your cells to do whatever your cells do with glucose, because Dr. White doesn't know, other than it does transport it. So whenever you eat a starch, you're making glucose, which is why in hospitals, they have to feed you intravenously. Did I say that right? I hope I did. Uh, they're giving you the sugar that's already been digested from the starch that's in your blood. And that's why it works, I think. So next time you eat a potato chip or French fry, and now I'm ruining it for you. No, I hope I don't. You're making it into glucose. Now, I mentioned earlier, and let me talk about this right now. A while back, and it's still been, I haven't heard much about it, but the food companies listen. Another number of parents groups and mothers groups were complaining the high fructose corn syrup and products you sell our children are causing all sorts of diseases in them, and like autism, and they had a whole list of things. And this is my personal opinion, I'm labeling it as such. I don't believe that. And why not? Because what happened was the some of the companies said, oh, we hear your pain, we're going to change it. And they took out some of the high fructose corn syrup, and what did they replace it with? Sucrose. Now, why am I saying I don't think it's the fructose alone that's causing it? Because let's look at the following. Let's say you have a product with a lot of sucrose in it. And what happens, which many years before high fructose corn syrup was the sweetener in foods. And what's sucrose? It's glucose and fructose linked together in an acetal linkage. As you learned here, you break it down to the aldehyde or ketone and alcohol. In this case, you get back glucose plus fructose, and you should know this. Hint, don't you like it when I'm subtle? I do. But if you think about it, if you replace fructose with sucrose, when your body breaks it down, you're still getting a lot of fructose in your body. And therefore, that's why I don't believe that, because before fructose was used, they used sucrose, and you're still getting a lot of it. What I do believe is, and this is personal opinion, I know from a fact, that if you put a lot of any sugar in a product, it's a lot of calories. And you eat enough, you're going to be overweight, and that's going to cause a lot of medical problems. Luckily, I'm still trying to get rid of my overweight, especially my pandemic weight. Don't ask, don't ask. But, anyways, when you eat sugar, sucrose, or high fructose corn syrup in a product, both of them in your stomach, you're making a lot of fructose. And if you go back 50 years or so, where people coming down with the illnesses they claim nowadays children are getting due to high fructose corn syrup? And the answer is, I don't think so. Or wasn't publicly out there, but I don't buy that. I think it's the calories. If you eat too many calories and you get overweight, then you're going to have a lot of medical problems. And that's the part. And that's my opinion. I'm labeling as such, so you know so. Now, if you look at online somewhere, and I picked this long ago, here's a glucose. Here's a glucose. And notice in starch, the stereochemistry of this bond, the acetal bond, is both below, the oxygen is below the ring. This bond and this one are below a plane of the ring. And this is starch. And hydrolysis, what we mean, is acid and water in your stomach. Now, it turns out cellulose, such as grass, hay, and other things, is made up also of glucose. Now, how many of you think you would stay alive if you had to eat grass to stay alive, or hay, or I'll teach you also paper? And the answer is no, you wouldn't. Why? Because cellulose in grass, hay, which cows and horses eat, and other animals, has a different type of bond right here. This is still a glucose. This is still a glucose. But now one of the bonds is above and the other is below, and that affects the stereochemistry. And because of this, this is a slower hydrolysis. One of the things I haven't talked about in this class is the rate of a reaction. Is it fast, slow? And organic chemical reactions happen at different rates, but I've not talked about it in this class. Well, it turns out this is slower, much slower. And how many of you have seen a horse or a cow or an elephant? And they have massive, massive stomachs, or a cow, and now I'm getting well beyond my knowledge of animal husbandry, have 4 stomachs. If you look at a cow, they're huge. Why? Same thing with a horse or an elephant, is because it takes a long time to break down the grass or hay or whatever they're eating. That's cellulose, plant material, and therefore they need more time to hold on to that material in their stomach. Our stomachs are not that big. I hope not. But anyways, they're not. And you don't keep this in your stomach long enough. This is faster, and therefore we can break it down. And we can break it down. And that's the difference. Now, cellulose is D-glucose in a linear polymer, 1,4 linkage like we saw before, but that one oxygen linkage between the two glucose molecules, I think one is called an alpha linkage and the other beta, and I always forget which is which. Now, let's have some fun with cellulose. And I'm going to turn the switch off, but now's the fun part of the semester where you've learned enough organic chemistry, we can go out in the real world and have some fun. That's not what I want. Everybody's on, probably not. Everybody see cellophane on your screen? How many of you ever bought candy or other things that have that real crinkly plastic that tears real easy around it? It's called cellophane. How it got that name, I'm not sure, but cellophane, someone found the reaction if you take cellulose and react it with sodium hydroxide and carbon disulfide, you make this molecule. And cellophane is that crinkly, here they have some picture. Oh, they took it away. They used to have it, you know how you can buy certain crackers or cookies in that clear plastic that's real crinkly, or candy, and that's cellophane, and that's made from cellulose. Now, long time, no, not that long ago, I showed you this reaction. If you take an alcohol and react it with ethylene oxide, you get a molecule that's a ether alcohol. Well, if we look at does everybody see cellulose on the, see the structure here? This is a cyclic form and a Newman projection. And here's the bond between the different glucose molecules, like I showed you. Notice on the molecule, you still have hydroxyl groups. Guess what? You can react those with ethylene oxide. And we do. And we call that hydroxyethyl cellulose, which has this structure where the R group on the alcohol, the H, has been replaced with CH2, CH2OH. So you have O, CH2, CH2. So you take cellulose and react it with ethylene oxide, you can make this. And hydroxyethyl cellulose is a very good thickening agent because it will hydrogen bond with water better than cellulose. And if you look at certain food products, you can find hydroxyethyl cellulose in them. Now, let's go to one that's not a food project, because I can talk about it because it's organic chemistry. If you see on your screen, does everybody see water, glycerin, and everything? KY jelly, which is a personal lubricant, which I'll tell you it's for a personal, how should I say, event between people, and I'll leave it at that. If you notice, it has water, glycerin, hydroxyethyl cellulose. Now, this next thing, the chlorohexadiene gluconate, is a preservative. Same thing with the next one. And the next one is the thickener, sodium hydroxide, adjusts the pH. But the water and glycerin hydrogen bond to hydroxycellulose and make it this thick, viscous material, which is a good lubricant. And if you look at things, certain, I'm not sure if they put it in ketchup. Hold on one second. I was almost positive. I'm pretty sure they put it in there, a small amount, in ketchup, hydroxyethyl cellulose. Now, one of the reactions I didn't show you, now, test number one, I showed you this reaction. Which puts a nitro group. Now, do not try this at home. And you can convert an alcohol, which I didn't teach you, to a nitro group. And we can now, and back around the turn of the century, 1900, I gotta remember which century, because now I could say turn of the century, that was 1999 to 2000, but I'm talking about 1899, 1910, around then, they found if you took cellulose and nitrated it like this, you form nitrocellulose. And that's where some of the hydroxyl groups on the cellulose, which is these hydroxyl groups, you could convert into NO2. And you had nitrocellulose, which was a nice polymer material that if you put the right chemicals on, you could use to make movies. And for many decades, the material, the film that was used to make the movies shown in movie theaters was nitrocellulose with a film base on top. What is the problem? How many have heard of trinitrotoluene? It's not that stable molecule, TNT. Well, nitrocellulose over decades isn't that stable either. In about the 1950s or 60s and early 70s, a lot of the archives with old films from the 20s and 30s were catching fire because the nitrocellulose was unstable and took off, exploded. So there number of decades now, there have been projects where all those all nitrocellulose films were converted to, guess what? Better things captured on more stable film or now electronic media. Well, I'm really getting into the good stuff now. How many of you are familiar with cotton? And cotton is a nice fiber, better than polynylon. Did I tell you the polynylon disco time clothing? They made nylon, it didn't breathe. How can, but they say cotton is breathing. No, I don't hear it inhaling. What do they mean by that? Well, cotton, if you notice, cotton is really cellulose from plants. You see that on your screen here? Let's see if I can get it bigger. No, here. And this is cotton. Now, one of the things they say, it breathes. And what does it mean by that? Hopefully you all remember from your general chemistry, molecules with oxygen with a hydronic and hydrogen bond. And what's the one thing when they say it breathes, what they're really meaning is it wicks away moisture from your skin. And what is moisture from your skin? Water. And the cotton, hydrogen bonds to your water and from you when you perspire. By the way, men sweat, women perspire. But anyways, and that's what they mean by breathing. And when you have something like nylon, which doesn't have this, it won't, and you can't get rid of, wick the moisture from your body. And it makes it quite uncomfortable. Trust me, I had nylon shirts from those disco days when everybody wore them. That's all you could buy. It's like being in a wetsuit. You really were uncomfortable. Now, how many of you ever had towels that after a while don't work as well? They don't absorb the moisture from your body when you go to dry your hands. What's happening? Well, you've been using a fabric softener. And if you have a fabric softener, it's, remember, like dissolves like, and polar things are attracted to polar things. Well, quaternary ammonium salt has a polar head, nonpolar tail. Long tallow groups, which are not soluble in water. Now, the hydroxyl groups on the cotton, which you use a fabric softener to stick on, makes from the long alkyl groups, oh, it's nice and soft and anti-static. Well, if you use it over enough time, you start blocking all those hydroxyl groups on your towel. And guess what? It won't hydrogen bond as well. And that's how a towel works. Oh, I forgot to tell you. Have you ever wondered the magic how you have a paper towel or a regular towel and you got wet hands? You go like this on it, all of a sudden they're dry. How does that happen? Magic? No. Hydrogen bonding again. So next time you see a friend wiping their hands on a towel to dry them, you can tell them, you know, you're doing hydrogen bonding of water to the towel to get it off your skin, which doesn't hydrogen bond as well. Organic chemistry is all around you. Oh, I forgot to tell you. Eh. Now, if you have old towels or not that old that aren't absorbing as well, how do you get them back to new condition? Well, it's simple. You wash it once or twice after you've used it, and you don't use a fabric softener. What that does is it strips off the fabric softener, and it's still going to be soft, but not as soft with a fabric softener. But you'll now be able to hydrogen bond, and after washing it once or twice without a fabric softener, then you can go back to using a fabric softener. Once it gets not as absorbent, by the way, that's called re-wet. Yes, I've worked with fabric softeners. An important thing is to try and design one with a low or a high re-wet that doesn't block that hydrogen bonding, which I did in my second patent. And anyways, that's all organic chemistry. All right, let's go through something you should know. Can I draw it any bigger? Leaving my class, I would like you to know how to describe with words and a general reaction a couple of things. And we've gone through two of them, so now I can talk about it. Name, describe, all right, I'll decode this. Describe with words and a general reaction what happens when you eat a food with fat or oil. If you had a potato chips, you put butter on your toast this morning, you had bacon or hot dogs or hamburgers or whatever, how do you describe that? Well, what's the functional group in fats or oils? And that's an ester. And what happens in your stomach? Acid, hydrolysis of an ester. Fat or oil is a triglyceride triester. And you learn for test number 3, the general reaction, ester plus acid and water and you can put that above the arrow too, you get back the carboxylic acid plus the alcohol you would have used to make that ester. So next time you eat anything with fat or oil in it, like you put butter or mayonnaise on. Dr. White is a mayonnaise freak. I love mayonnaise. Hellmann's is the best. One of these years, I might even try making my own. Nah, it's easier to just buy Hellmann's. But anyways, you should know how to describe with words and a general reaction what happens when you eat a fat or oil. And a functional group, because there's an ester in it, is what happens is acid hydrolysis of an ester. And here's the general reaction. Now, the other new thing you learned today is what happens when you eat a carbohydrate. And what functional group holds glucose together in carbohydrate starches? And that's an acetal. And so how do you describe it? Well, you eat it, you chew it, you swallow it. In your stomach is acid and water. We call that acid hydrolysis. Of an acetal. And that's how you describe it with words when you eat a carbohydrate. And for test 2, I'll put down both acetal or ketal. Acid and water. You could have put it +2 plus acid and water. You get back the aldehyde or ketone you would have used to make that acetal or ketal plus the alcohol. For those who want, you can put the 2 there. I don't. I do that because a couple of years ago, I had these 2 twin sisters. They were identical twins. It took me a while to figure out. One had a slight blonde streak she put in her hair. The other never did. Then I figured out, and also their emotional makeup, their personality, I finally learned. And both got upset if I didn't put that 2 there. So I didn't want 2 twins upset at me. I got in the habit of putting it in. So when you eat a carbohydrate, how do you describe with words what happens when you chew, swallow it, and you digest it? That's acid hydrolysis of an acetal. What's the general reaction? You learned that for test 2. Acetal, ketal, acid, and water gives you an aldehyde or ketone plus an alcohol to make that. And that's how you do it. Now, next week, I'll be going through, there's not too many next weeks. Oh, I just had a sad thought. Our semester's almost over. Our time together is almost gone. Oh, Dr. White, actually, it is sad. Hope you're having a good time. I am. Anyways, I'll be talking about later on, not today, what happens and how you describe it, words and general reaction when you eat a protein. And I think I've by then covered all these traditional 3 food groups, fats and oils, carbohydrates, so we'll do protein. Now, like I said, these are 2 things, and I'll go through protein you should know. It even says this, leaving my class, because all of you are in some way, I believe, health-related majors, and you should know how to describe with words and a general reaction when you eat a fat and oil, which has an ester functional groups. It's acid hydrolysis of an ester. Here's the general reaction. Ester, acid, and water gives you a carboxylic acid and the alcohol you would have used to make that ester. When you eat a carbohydrate, what's linking glucose together? and that is an acetal linkage. So that's acid hydrolysis of an acetal, and here's the general reaction. Acetal, acid and water, gives back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used to make that acetal or ketal. Now, while we're getting along stuff you should know, leaving my class, I think this is a good time to talk and remind you, you should know how soap works. And the first thing you should know is the structure of soap. And soap has a long nonpolar tail and polar head. Whether it's liquid or bar, it's the same thing as a polar head. And the key thing when it comes to how does soap work is the following. So key, I'll write it in big letters. Like dissolves like. And what that means is things that are polar are soluble in polar things, and things that are nonpolar are soluble in nonpolar things. And if you mix the two together, nonpolar and polar, they're not, as you learned from the lab we did last week. And when we come to this, water is polar, and you should know that. Dirt and grease are nonpolar, which is why it's not easy to get dirt or grease off your hands or whatever with water alone, which is why we use soap. And if I had a piece of dirt here, and you should know this, when you use soap, the nonpolar tail is attracted to the dirt and the polar head stays away from it. And you use a lot of molecules, and I'll just do a few soap molecules, but it surrounds us completely. And you should know how to draw a micelle. And what is a micelle? And this dirt particle surrounded or greased by soap becomes a micelle. Now, water sees the micelle and says, oh, micelle, and it only sees the outer polar heads, says, micelle, you're polar, I'm polar, let's go down the drain together. And they do. And that's how soap works. Let's go through it again. I think it's that important. You should know the structure of soap is nonpolar tail, polar head. The most important thing, how soap works is like dissolves like. And water is polar, dirt and grease are nonpolar, therefore they're not going to work together. But when you use soap, it forms a micelle, which you should know, excuse me, and guess what? The micelle, which the outer part is all you see are the polar heads, water looks at the micelle and says, hey, I'm polar, you're polar, let's go down to drain together. And lo and behold, your hands are clean. or whatever else. And when I was taking my morning shower, I was probably the only one in Northern Illinois, maybe, who was thinking, wow, I'm making my cells when I'm using the soap. And I was. Now you know I'm an organic chemist. All right, before I move on, any questions? All right, just a quick reminder, don't forget tonight I have my office hour if you have any questions. Don't forget about the extra credit project. And I'm not finished yet, but we may end a little early today, but I still want to go through one more thing to help you out. And don't forget the extra credit project. And on Wednesday, we'll do the lipids. And essentially, I finished carbohydrates. And next Monday, we'll do the carbohydrates problem set. Now, one thing that I think I forgot to teach you was something I came up with myself. And that is, have you ever had to clean a bathtub with a lot of scum on it and the walls too? And it's probably the worst job in the world. I'd rather clean toilets than clean a bathtub. There is easier. Even that, there are better things in life. But cleaning in my house, what's the bottom of the very bottom? Scrubbing out a bathtub. And a couple of years I was doing that. A number of years ago, I'm thinking, there must be a better way. You're an organic chemist. Think about it. And I thought about it and said, what's bathtub scum? This won't be on a test, but you can use it at home. When you have soap like this one, if you use bar soap, it's not as prevalent with liquid soap. This is long tallow group, long nonpolar tail, polar head. Well, in your water, there's calcium cations. If I take two of these, and you saw that in the lab we did, not last week, but the week before, and this is your soap scum. Well, some people say use vinegar and all that, but vinegar is a very weak acid. And CLR I don't like because I don't know what's in there. And strong chemical products that I don't know what's in there, I don't want to use. So how do I break this down? Well, there's another acid that's available. And this is called oxalic acid. And notice it's a diacid, di meaning two, one, two carboxylic acids. And it's a solid at room temperature. And what it does, and this will never be on a test, but I thought I'd teach you this. It does an ion exchange. You get back tallow acid. And depending on the pH of your water, this might be a carboxylate anion. And you get and there's no end here. I really don't need the brackets, but I just wanted to show you this all one molecule bonds this calcium oxalate, a carboxylate anion of that. You're probably saying, well, where do I get oxalic acid? At your local supermarket. No, I've never seen it sold there. Well, let me show you a great product. And unfortunately, I don't get kickbacks from them. All right, let's see if I switched over. Yep. Everybody see the gold cans on your screen? This is Barkeeper's Friend. I've got a couple of cans in my house, and this is a mixture of oxalic acid and sodium lauryl sulfate, which is a soap. And I think it's got some other ingredients in it. Let's see. Hold on. Everybody see on the screen? It contains some feldspar, which is a linear sodium disulfide. This is a soap and oxalic acid. Don't keep it on your hands, obviously. So how do you use this? Well, what you do is, and here's what works for me, and I've got to do it this weekend. I hate doing the bathtub, and I let it go until it's the point where, yeah, you better clean that scum off it. And it's pretty not crusty, but if I had to scrub it, like with Comet or whatever, it would be a 45-minute job at least. Not anymore. First of all, Dr. White has a shower head that's detachable. How many of you are familiar with that? If not, you can just take a small little bucket or sponge. I take some hot water and spray the walls and the bathtub real quick. Then I take oxalic acid and sprinkle it on there and rub it just a little bit to make sort of a paste over with a wet paper towel. Sponges get spoiled real quickly, so don't use a sponge, use some paper towels and just rub it on there. Then I go sit down and read a book or something for about 10, 15 minutes. Then I come back and with a wet paper towel with dampen, you just rub it a little, or if it's really, really bad, you know those 3M green pads? You cut them in smaller ones so you don't get foul the whole thing, and you just rub it like this. It usually, when I do that, takes me about 5-6 minutes to do the walls in the tub when they're heavily encrusted. And then you take the spray nozzle, because I have this, and I spray it down the drain, and it breaks it up like that. And that's using organic chemistry. And what you're doing is an ion transfer. Now, the other thing is, Barkeeper's Friend is really good. Have you ever had a frying pan with a lot of yuck in it and you're trying to get it clean? Well, the first thing is, how many of you have ever heard of deglazing a frying pan or something? And generally in cooking, you'll put some wine or something in there. Well, years ago, Dr. White said, I'm tired of using steel wool and all that. And now I have all clad stainless, but still you got to be careful on certain things. I don't want to scratch it up. The first thing I do is I'll put some water in there and boil it. And let it go for a couple of minutes. And you take a spatula, I have plastic ones, and it comes, most of it comes off real good. Now, once in a while, you got stuff that won't. And sometimes in my all clad oven pan, even though I use aluminum foil in there, some stuff gets there. And what I do is rinse it with hot water, sprinkle in some Barkeeper's Friend, and then put a paste, let it sit for about 5 minutes, and it comes right off. That's again the acid breaking down the fat, any carbohydrates, just like I just showed you, like in your stomach. I'll teach you later on, acid water breaks down protein. And that's my helpful hint for today. Now, do I have to, oh, I got time. Did I talk about hair and grease remover in here yet? Nope. All right. Let's just, when I first bought the house I'm in, that was about 20 years ago, more than that now. Wow, time flies when you're having fun in life. But anyways, I just bought the house. About 3 weeks after I moved in, my kitchen sink stocked up. I said, the previous owners, they must have poured grease or whatever down there. You never pour grease or fat down your sink. It's going to clog it up. I put it in a Ziploc baggie in my garbage can. But, so I figured, let me get the Roto-Rooter guy out. Let's do it right. So I called up a rotor-rooter guy, and he comes out, does it, and it's unclogged. 2 weeks later, less than that, it's clogged again. Well, it had a guarantee, comes out, and I was working full time in the chemical industry, and it wasn't the money I was wasting. It was I had to stay home to wait for this guy. I had work to do. As a senior manager, things have to get done. Well, anyways, he does it again. I thanked him for coming out promptly. And a week or so later, it clogs up again. And he comes out again. Now he says, all right, I'm going to get it this time. And he holds up this bottle of chemicals that he never used before, says, I'm going to pour this down and let it wait, and then we'll root it again. I said, can I see the bottle? I'm a chemist. I look at that and I figure, that's a joke. It just had soap in there and some other things and surfactants that wouldn't do the job. So guess what? It plugged up again within a week or less. I figured, nah, I'm not going to call him. It was a bad experience. I've learned my lesson. So I went to my local home improvement, which in my case was Home Depot. And they have a whole long shelf of all these drain cleaners. And being an organic chemist or a chemist, I picked up some of the bottles. Oh, acid, hydrochloric acid, sulfuric acid, and they're all acids. And I'm wondering what I use. And one of the nice people working that store, and this is the one in Barrington by my house in Schaumburg, came up, can I help you? I said, sure. All these drain cleaners, and I asked, which is the one the plumbers used? And without thinking, just like that, he points, this one. I pick up the bottle, and also I learned an important lesson about Home Depot. And I picked up the bottle, and instead of seeing acid, I saw sodium hydroxide, potassium hydroxide. I said, oh, this one's got a base and they're acids. They said, no, that's an acid too. And I said, I got a PhD in chemistry. I think I know the difference between an acid and base. He said, no, that's an acid too. And I figured, guess what? He's helped me. I'm not going to debate acids and bases when I know he's wrong in Home Depot. But I took it home and it worked. And let me show you what worked. By the way, I don't get any kickbacks from this product or Home Depot. I wish I could, but I don't. Everybody see the black bottle with the label on there? It's now called Instant Power. It used to be just here in grease remover. And this stuff, I keep a large bottle in my house. I keep the 67.5 half gallon. And I've used it in the last 20 years, I think 3 times. And it's sodium potassium hydroxide for grease and oil in your kitchen. It does a base hydrolysis to break it down, as opposed to in your stomach, you use acid, and it works quicker. And this stuff, follow the instructions. It's a hazardous chemical, so I put on safety goggles or glasses, which I have in my home. I always wear a long sleeve top or a lab coat, and it works great. It also works great in the bathroom. I've had students who've come to me after I teach, what was that you told me? And they have clogged bathroom or tubs, and this works beautifully. Now they say let it go about 15 minutes. If it's really bad, clogged after you pour it in, I let it go a half hour. And then instead of turning the water on from that tap in that sink, from another sink or my utility sink, I'll get a bucket of very hot water, because temperature rule of thumb, for every 10 degrees C increase, the reaction rate doubles. That helps clean out, and then you let it run for a little while. And I've been in this house almost 22 years now, and about 3 months ago, my bathroom sink in my main bathroom upstairs started running real slow. I figured, well, after 20 years, I bet it's clogged up a little. Took this stuff, put I think it's a cup down there, I let it sit because it was old. It'd been here so long, about an hour. Then hot water, and I don't expect to see a problem for many years. My brother-in-law's used it in their house, a lot of students, and that's what we got. Oh, with that, I'm done for today. I hope you enjoyed. We're now getting into the juicy stuff where you're learning what you've learned in general or reactions is happening all around you. You use it for good stuff. And if you ever have any questions about how to clean your bathtub or drain, always feel free to email me. No charging at all. And with that, I went a whole 3 minutes. I hope you'll forgive me, but I'll see you on Wednesday. Don't forget, I'll go through the fats and oils problem set. Don't forget to hand in your lab. And with that, gain gesund. I'll see you on Wednesday unless you stop by for my office hour tonight. Bye.